in this video we are going to explain the chapter 5.1 that is called eigenvalues and eigenvectors. So, the main definition of eigenvalue is if ax is a scalar, multiplication of x x is equal to lambda x. So if the scalar lambda is called an eigenvalue of a and x, so if this is satisfied, this is an eigenvalue. Also, in another color I want to explain an eigenvector. Well, if A is a n times m matrix, then a non-zero vector, that is in Rn. Rn. Well, this is called an eigenvector. So, for instance, let me explain an example of an eigenvector and an eigenvalue. So, for example, if we have a matrix, for example, A equals to a 2 times 2 matrix, it's equal to 3, 0, 8 and minus 1. So if we want to make an eigenvector, we can see that it needs to be a non-zero vector of the same n, so it's 2 times 2, so we made a vector of 2. So a vector could be 1 and 2, for example. I choose this because later I will use it for the eigenvalue explanation. So, for example, this, as we know, is an eigenvector, so we can use it to determine an eigenvalue. So, for example, for the same matrix, we make a multiplication. So, for a corresponding lambda equals 3, and you are going to see why. The first the matrix we need to multiply by the vector. That's why it needs to be the same 2. So 2 times 2, and this a 2 times 1 vector, so it can be multiplied. This is going to be, it's 3 times 1, it's 6, and 0 is 6, and 1 times, 8 times 1 is 8, and 2 times minus 1 is minus 2, and this is minus 6, and this is 3. Yeah, and for instance, this is 3 times x. And depending of the sign of the magnitude of the eigenvalue, lambda, this eigenvalue lambda, the ax equals lambda x, compensates the strength x by a factor of lambda r reversal direction if lambda is negative. For example, let me draw this because it's difficult to explain. If lambda is between the values 0 and 1, lambda, and we're going to see something like this in the vector. This is the starting point. This is lambda, for example. Could be at the middle, at the edge, doesn't matter. And this is x. So if it's between these, that is positive, you're going to see this. If for example is from -1 to 0, so it's a negative value, the origin is going to be like here, x is going to be here, and then here is going to be, well, lambda x. So let's go to the example 2 to clarify all of this. The example 2, first we need to tell about the theorem of the book, the 5.11, and says that, let me write this here, 111, that if A is an M times N matrix, so for instance you can see it's in different order. So if M times N matrix, then lambda is an eigenvalue of A. Okay, if and only if it satisfies the following equation. So that equals lambda minus A. So, and this is equals to 0. This is called characteristic equation of A. So let's explain this. For example, if we use this equation, lambda times I minus A needs to be equal to 0. So in our last example, we say that the matrix A is equals to this, so we're going to use it, and we need to substitute the values with the corresponding lambda. So A is going to be lambda minus 3, lambda minus 8, 0, and lambda plus 1, because the sign. So this, for instance, is going to be equal to 0 because the theorem says that. So if we make this, the determinant of this, that is this times this and this times this is going to be, the 0 destroys this lambda minus 8, and we only have lambda minus 3 times lambda plus 1, and this is going to be equal to 0. So if we solve this, you can see that lambda could be 3 and minus 1. Okay, let's go forward, and next an example of eigenspaces. Well, for basis for eigenspaces, it could be this. I'm going to write it here because I don't have so much space. And I'm going to write the example. If we have a matrix like -1, 3, and 0, we could use this theorem also, and for instance this is going to be lambda plus 2, lambda minus 3, lambda, and here it's going to be lambda minus 2. Well, I forgot these lambdas doesn't go here. So with this we can start with the determinant. So we're going to have this lambda times lambda plus 1 because of this multiplication, and this is minus 6. Well, yeah, this is minus 6, but it's equal to lambda minus 2 and lambda plus 3, and this needs to be 0. So in this case we can make a general solution, I think that's called, that is lambda plus 1 minus 2 minus 3 and lambda is what we have here, that it's multiplied by x1 and x2, and this is equals to 0 because we already know the theorem. So this, in this case, if lambda is 2, we can say, for example, the substitution of this, that is 3 minus 2 and 2, and this also is the solution for this. That needs to be equal to 0 if this is an eigen space, because it has an eigenvector and also an eigenvalue. And can be written like for example, if x1 we call it t and x2 also we call it t, so this could be transformed into a matrix with 2 ones. And for that, if the basis is corresponding to lambda 2, so we can say that what I'm going to write here, a minus 3 and 1, and this is the basis corresponding if lambda is equal to minus 3, for example. So this is the result. And now we know how we know the definition of an eigenvalue and eigenvector, so we're going to go forward with the chapter 5.2. So let me pause the video and change the quality. Hey, we are back. So now we're going to talk about the chapter 5.2 of the book of linear algebra. So this chapter is called diagonalization. And it's called like this. Well, first we need to talk about what we're going to see in this chapter, and we're going to see how you find a basis. Find basis for Rn, and spoiler alert is that this is made by using eigenvectors of an n times n matrix. So we're going to explain that. Well, the matrix diagonalization problem begins with this, that A is going to be same as P to the minus 1 times A times P. And well, this P can be, this can be written also in like determinants. So our way to write this is going to be determinant, for example, of B. This could be whatever matrix we want. It's going to be the determinant of this I am drawing the ways to write the rule. And this is going to be also that of p to minus 1 to determinant of a and determinant of p. Okay, and this now can be written as that of p because of the exponent, and that of a and that of p. And if we see this, the determinant of b is going to be the determinant of a. So, in general, any property that is preserved by similarity transformation, that this is called similarity transformation, it's going to be similarity invariant. So here doesn't vary. So I don't know how to say. Well, let me use another marker. And well, first we need to write the similarity invariance rules. For that is a table, but I'm going to be quick in that. For example, the determinant needs to be, well, the same determinant. We see this. Also the same. Also the integrity needs to be, well, if A is invertible, so P times A times P needs also to be invertible. So 2 invertible, the 2 needs to be invertible. Also, the rank, they need to have the same rank. Also, the nullity needs to be the same. And the trace needs to be also the same, and in this case is characteristics to be polynomial. And for instance, we need also 2 more rules. The one of the eigenvalues and the eigenspace dimension. Well, they need to have the same eigenvalues, and this is also the same. Well, and let's go forward. With this in mind, we can use the first definition that I'm going to read, and is if A and B are square matrices, then we say that B is similar to A if there is an invertible matrix, such as, and this was we are talking about here, that we can resume the first definition as B is equal to P times A times P, and this is because well, the P doesn't make an effect here. Also, in the definition 2 says that a square matrix, keep in mind that all the matrices here are square. So, square matrix of A is said to be diagonalizable if it's similar to some diagonal matrix if there exists an invertible matrix P, this P, that such as also this, if there is any P that can make this, this a diagonal. So for example, a quick example is that 2, 2, 3, 0. If there exists any P that can make this that it's diagonal, for example, well, it's a bad example, 7 for example. This is diagonalizable. Okay, so let me mention also two theorems. For example, the theorem 5.2.1 says that if an n times n is equivalent if the A is diagonalizable. So first, A is that if is diagonalizable, and also if A is linear independent, to his eigen vectors. Go forward with the 5.2.2 theorem that says that, well, if we have lambdas, for example, lambda 1, lambda 2, and to the lambda k, are distinct eigenvalues, each one, of a matrix A. And if vector 1, vector 2, and that to vector k are corresponding eigenvectors, then we can say that this is a set, that this set is linearly independent, and also, and the second thing that the theorem says is that an n times n matrix with distinct eigenvalues, it's the diagonalizable. So indistinct eigenvalues. Okay, it's diagonalizable. Also, well, we are going to talk about the steps to diagonalizing a matrix. So I have, well, the first step is that searching for n linearly independent eigenvectors. So search for n linearly independent eigenvectors. Okay. Well, we have some ways to do this. One is to find a basis for each eigenspace. So, first one, 1.1, find a basis for an eigenspace. Well, step 2 is to ascertain that the matrix is diagonalizable, then form the matrix P